Today we are going to do problems on lasers. This is the part 1. So let us get started. So we'll go to the first problem. So these are simple problems, and these kind of questions may be asked in the entrance exams. So this is the first problem. I have not written problem here. So this is the first problem. So this is the first problem. Let's change the color. Okay. So the first problem is the number of photons emitted per second from a 1 watt argon ion laser operating at 488 nanometers is 2.46 into 10 to the power 18. We have to show it. We have to show that from a 1 watt argon ion laser operating at 488 nanometer, the number of photons emitted per second is 2.46 into 10 to the power 8. This is simple. Power is given here. This is the power, and energy of a photon is hc by lambda. So divide by power and divide power by hc by lambda, and you get the number of photons. So with the next problem, the next problem is the spectral line of helium neon laser is 0.1 nanometer, a spectral width maybe, and the cross section of the beam is 0.01 centimeter square. If the power output is 1 milliwatt, then show that the radiation intensity per unit wavelength is, and we have the unit in which we have to express is watt per centimeter cubed, is 10 to the power 10. Okay, so it will be 10 to the power 10 watt per centimeter cubed. That will be the radiation intensity per unit wavelength. So simple. So we know this. We know the wattage, 1 milliwatt. So if we divide 1 milliwatt with, so if we divide 1 milliwatt divided by the area of the beam, then we get the radiation intensity. That is in terms of so we get radiation intensity in terms of so that will be in terms of per centimeter square, and then we divide it by the wavelength. So wavelength is given by 0.1 nanometer. So this thing has to be divided by the wavelength, and once we do that, what we'll get the answer. As simple as that. Next is a laser beam emerging from a laser tube operating at 80 nanometers, has a cross-sectional area of 2 millimeter. The diameter of the beam at a distance of 1 kilometer is approximately given by 10 centimeters. So we have to show it. So we have to show that the beam has a diameter. So the beam has a diameter of 10 centimeters at a distance of 1 kilometer. So the thing is, this laser tube has an aperture from where the laser is coming out. So due to diffraction effects, there will be divergence. So this theta is called the half divergence angle, and it is given by 2 lambda. Lambda is the operating wavelength of the laser, divided by pi w naught. W naught is the waist radius. So in this case, the waist radius is 1 millimeter. Another way of finding out theta is d2 minus d1 by 2I cell. So what is d2? Let's go to this picture. So this is my laser beam. So this is my laser beam is diverging, right? It will diverge because of the diffraction effects. So at this point, this is the diameter of the beam D1, and at a distance L from here, its diameter is D2. Okay, so what is theta? Theta is this angle. So theta is, so this is my laser beam, this is my horizontal line, so this angle is theta. So this angle is theta. And you can clearly see what is this distance? This distance is D2 by 2 minus D1 by 2. This distance, and this distance is equal to L into theta, where L is supposed to be very, very large, much greater than 1. If that is the case, then you can write like this. So you can easily see from here I get this theta. So here you can find out the divergence from here. Everything is given, so theta you can find out, put it here. For D1 you can put the waist radius, you can put the waist diameter, this is twice W0, and you will get D2. L is given, L is 1 kilometer. So this is another problem. The next problem is the dependence of Doppler broadened line width of a laser transition has a temperature dependence given by which one? T to the power half, T square, or T to the power minus half. Remember, a laser transition line is not of zero width, it is broadened, and it is broadened due to one of the effects, one of the reasons that it is broadened is because of Doppler effect. Because higher the temperature, greater will be the velocity of the atoms, and hence the transition line will be broadened. It will not be a very thin line, it will be having a width. So it should increase with temperature. This does not increase with temperature, so this is ruled out. So broadening is like this. So you have it has a Gaussian shape. Okay, this is a Gaussian shape. So this is where the peak is maximum, and this is the width. This is what we call the width of the line. Okay, so this is at a low temperature. If you go to higher temperature, then it is broadened. So this Gaussian shape may look like this at a higher temperature. So the width will be broadened. So this is where my central line is, and then on the left and right there will be lines of lower intensity. So this width actually goes as your T to the power half. So this is the correct answer. The Doppler broadening goes as T to the power half. Next we have another question is, when the refractive index mu of the active medium changes by delta mu in a laser resonator of length, it should be length L, I think, length L. The change in spectral spacing between the longitudinal modes of the laser is this. So what is the idea? Idea is we have a resonator, and here we have standing waves. So this is a resonator and the length is L. Here standing waves are created. Okay, standing waves are created. Standing waves are created. Here standing waves. So what is the condition for having standing waves? The condition for having standing waves is twice mu L. Standing waves means, so there will be, so a wave will go in this direction and get reflected, and then that is how we have standing waves. So the optical distance travelled is twice mu L, is it not? Twice mu L is the optical distance. This is the optical distance travelled. Optical distance travelled. Mu is the refractive index. This is the optical distance travelled. This optical distance travelled should be equal to an integer times lambda. Then only we can have standing waves. So from here it's easy. So you express lambda in terms of nu, and what you get is this. C is the velocity of light. Okay. So these are the, so for different ends you have different frequencies. So these are the frequencies that can be sustained by this resonator. So this difference between the frequencies is C by twice mu L. Between two adjacent frequencies is C by delta mu L, corresponding to delta n is equal to 1. Now if we change the refractive index mu to mu plus delta mu, so we can change the refractive index to mu plus delta mu, then in the new case the new spacing will be C divided by mu plus delta mu n. So what is the change in spacing? The change in spacing is delta nu minus delta nu bar, and you will get the answer. So you have to show that this is what the new change in, so this is the change in spacing of the frequencies, and the longitudinal modes, these are the longitudinal modes that are sustained by the laser. You now go to the, I think this is the last problem, or no, this penultimate problem. So we have a laser of wavelength 740 nanometers and its coherence time is 4 into 10 to the power minus 5 seconds. Show that the Q factor or the quality factor for the laser is this. So Q factor is given by central frequency nu divided by delta nu, spread in the frequency or width of the frequency. So greater the width, less the quality factor, that is the more energy that is lost by the laser. So higher the Q factor, better the laser is. So in this problem, nu I can easily find out from this relation, nu is equal to C by lambda. Coherence time is given, so from there I can find out the spread in lambda. So delta nu times lambda is around 1. So from here tau is given, delta nu times tau is 1. So tau is given here, coherence time 4 into 10 to the power 5 seconds. So I can find out delta nu, and I can find out this Q factor. We go to the last problem. A collection of n atoms exposed to a strong resonant electromagnetic radiation with Ng atoms in the ground state, Ne atoms in the excited state, such that Ng plus Ne is equal to n, total number of atoms. This collection of two atoms have the following population distribution. Ng is much less than Ne, Ng is much greater than Ne, Ng is almost equal to Ne, or Ng minus Ne is n by 2. So this is for this, we know these are the Einstein coefficients. So these are the Einstein coefficients we know. These are the Einstein coefficients. These are the Einstein's coefficients. Okay. So this is for stimulated absorption. Stimulated absorption from the ground state to the excited state. Absorption. Okay, this is for stimulated absorption. This is also stimulated emission from excited state to ground state. This is stimulated emission. Stimulated emission. And this is spontaneous. So these are the coefficients, rate of transition. These are rate of transition, and this is spontaneous. This is spontaneous emission from excited state to ground state. Spontaneous. So it can be shown that AG by BG is proportional to nu cubed. The stronger, the higher the resonant frequency. That's, we have two energy levels here. So this is the excited state, and this is the ground state. And this energy difference is given. So this is the energy level difference, and it is measured by the frequency nu. So stronger, higher the nu is, greater will be the spontaneous emission coefficient. And hence, what will happen? Spontaneous emission means it will relax from the excited state to the ground state. So what we will have is finally this. The population, this one, the population of the ground state will be, the population of the ground state will be much greater than excited state. So we'll stop here now, and we will meet later. Thank you.